Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU, Bhilai. In today's tutorial, we discuss about the spanning trees. So, spanning trees can be defined as a subgraph of connected, undirected graph G that is a tree produced by removing the desired number of edges from a graph. In other words, spanning tree is a non-cyclic subgraph of a connected and undirected graph that connects all the vertices together. A graph can have a multiple spanning tree. I will discuss in the next slides what is a spanning tree and how it will generate. A spanning tree will be generated by the graph. As we know, the property of the graph is a combination of the vertices and edges, and how it will be converted in a spanning tree we will discuss. So in this article we will discuss the spanning tree and the minimum spanning tree. But before moving directly towards the spanning tree, let's first see a brief description of the graph and its type. As we know the graph, already we discussed this graph in a graph theory introduction. We take the property and again we call the property, and then we understand the concept of the spanning tree. So a graph can be defined as a group of vertices and edges to connect these vertices. This type of graphs are given as follows. So now first one is an undirected graph. An undirected graph is a graph in which all the edges do not point to any particular direction. They are not unidirectional, they are bidirectional. It can also be defined as a graph with a set of vertices and a set of edges. Each edge connecting two different vertices. Suppose we having a two station like a A station and a B station, and we having only a single edge between A to B, but we can travel in a bidirectionally way. So for A to B also and B to A also by the same edge. We don't go for the another edge, waiting for the another edge from A to B and B to A. By the single edge we can travel in both direction because this edge is undirected. That's why we call the undirected graph. Now second one is connected graph. A connected graph is a graph in which a path always exists from a vertex to any other vertex. A graph is connected if we can reach any vertex from another vertex by following edges in either direction. This is a property of a connected graph. Next one is a directed graph. Directed graphs are also known as digraphs. A graph is a directed graph if all the edges present between any vertices or nodes of the graphs are directed or have a defined direction. Suppose we having a lot of station and we want to travel from one station to the another station. If we having a edge, but we have to cross check this is a outgoing edge or a incoming edge. If the particular station having an incoming edge from another station, it is we can't move from travel from that particular station to that station. When we want to travel from this station to this station, we have a edge as well as the directed edge also. So particular directed edge having suppose Delhi and Mumbai two station, we having edge Delhi to Mumbai having a edge, but direction is given Delhi to Mumbai. So we can travel only Delhi to Mumbai, we can't travel from Mumbai to Delhi. If we want to travel Mumbai to Delhi, we can create or we can design another edge from Mumbai to Delhi. So in this way we can understand the concept of a digraph. Now let's move towards the topic of spanning tree. So what is spanning tree? A spanning tree can be defined as the subgraph of an undirected connected graph. It includes all the vertices along with the least possible number of edges. If any vertex is missed, it is not a spanning tree. A spanning tree is a subset of a graph that does not have cycles, and it also cannot be disconnected. So, three major points when we are talking about this spanning tree. First thing is that when you considering a spanning tree from a graph, you have to cover all the vertices, or we can say all the nodes or stations. Second thing is that when you designing this spanning tree, the cycle should not be formed. That should be a cyclic order. So, say this is a second property, and we have to find out the minimum cost between when we traveling from one place to the another and covering all the vertexes. This three property we covering on the spanning tree. So, basically this property we can understand the concept how we design the spanning tree. So, a spanning tree consists of n minus 1 edges. Suppose we having a 3 vertices, so definitely n is equals to 3. So, the minimum number of edges we require, that is a n minus 1, it's a 3 minus 1, that is called a 2. Suppose we having a 3 vertices A, B and C. Suppose A, B and C, so 3 station over there, and we have to connect all the 3 vertices by a 2 edges only. So, when we covering n minus 1 edges, it should be a part of a spanning tree. So, where n is the number of vertices or nodes, edges of the spanning tree may or may not have weights assigned to them. All the other possible spanning trees created from the given graph would have the same number of vertices, but the number of the edges in the spanning tree would be equal to the number of vertices in the given graph minus 1. A complete undirected graph can have n minus 2 number of spanning trees, basically n multiplied by n minus 2 number of spanning tree, where n is the number of vertices in the graph. Suppose if n equal to 5, it means vertices equal to 5. The number of maximum possible spanning tree would be that the 55 minus 2, the 5 multiplied by 5 minus 2, that is a total 125. If you are having a 5 nodes, it should be a 125 possibility to generating a spanning tree. So, before we understanding, we have to understand the application of a spanning tree. Basically, a spanning tree is used to find a minimum path to connect all nodes of the graph. Suppose of the common applications of the spanning trees are listed as below. We can use spanning tree in a cluster analysis. When we performing some project, we have to design a database in a cluster way. We go for this, we can use this technology, this concept. Second one is civil network planning. Third one is computer network routing protocol. We can use this spanning tree concept in all these applications area. Now, let's understand the spanning tree with the help of an example. So, suppose this is a graph. We having a lot of vertices like a 1, 2, 3, 4, 5 vertices, and all are connected some edges as well as the weight also given over there. So, before we are converting a spanning tree, this graph is a cyclic graph, because when we are starting from any vertices, we reach that station via any cyclic graph also. So, it should be not a part of a spanning tree. It is a graph, but it is not a spanning tree. So, as discussed above, the spanning tree contains the same number of vertices as the graph. The number of vertices in the above graph is 5. Therefore, the spanning tree will contain 5 vertices. The edges in the spanning tree will be equal to the number of vertices in the graph minus 1. So, we can say there will be 4 edges in the spanning tree. Some of the possible spanning trees that will be created from the above graph are given as follows. Suppose as per the diagram of this particular graph, we can generating this 3 module. This is not a cyclic. We are talking about the first one, first spanning tree. Here we take all the vertices A, B, C, D, E, but it should be connected. We don't connect A to C, because when we connect A to C, it should be a cyclic order. That's why we don't connect A to C. And the second example, spanning through, we disconnect the A to B, rest of the edges we will connect. And the last one is we don't connect B to D. As like that, you can one by one, and you can free one edges in a particular graph and you generate a spanning tree. When a cyclic form will be created, it's not a property of a spanning tree. The spanning tree should be a cyclic graph. So the properties of spanning tree are, some of the properties of the spanning tree, like there can be more than one spanning tree of a connected graph. A spanning tree does not have any cycles or loop. A spanning tree is minimally connected, so removing one edges from the tree will make the graph disconnected. As well as a spanning tree is maximally a cyclic, so adding one edge to the tree will create a loop. There can be a maximum n to the power n minus 2 number of spanning trees that can be created from a complete graph. A spanning tree has n minus 1 edges, where n is the number of nodes. If the graph is a complete graph, then the spanning tree can be constructed by removing maximum e minus n plus 1 edges, where e is the number of edges and n is the number of vertices. Suppose we are having a 5 vertices and 4 edges, 4 minus 5 plus 1, like in this way. So a spanning tree is a subset of connected graph G, and there is no spanning tree of a disconnected graph. So we're talking about the minimum spanning tree. Now we start the minimum spanning tree concept. So there can be weights assigned to every edge in a weighted graph. However, a minimum spanning tree is a spanning tree which has minimal total weights. In other words, minimal spanning tree is the one which contains the least weight among all other spanning trees of some particular graph. We can understand by this simple example. Here we having a 4 vertices A, B, C, D, also putting some weightage like 5, A to B 5, B to D 2, D to C 3 and C to A 6. This is called a weighted graph. Now, what we have to convert this graph into a spanning tree. So there are a lot of example, lot of graph here we showing. The first one we disconnect B to D. Now for second one we don't disconnect A to B. Third one we disconnect C to D. Then last one we disconnect A to C. The maximum kind of a possibility over there. When we disconnecting one by one, we have to calculate the sum of weight also. In the first one, we calculate the weight, that is the 14. Then next one is 11. Third one is 13, and last one is a 10. The minimum weight in amongst all the cyclic graphs, the last one, that is called the sum equal to 10. What we cover the edges, all the weights of the particular edges, when we sum of all the weight of that particular edges, that total sum is 10. That's why we are considering, when we find out the minimum one, when we could go for the last one. If we want to find out the maximum, we go for the first one. That's completely based on the weight of the edges. So the minimum spanning tree that is selected from the above spanning tree from a given graph, that's the last one, the total sum is equals to 10. Now we discuss about the application of minimum spanning tree. So the application of a minimum spanning tree are given. First one, minimum spanning tree can be used to design water supply network. If the cost is really, if you short the distance from source to destination, definitely network cost will be reduced, and definitely it will affect your cost also. So minimum spanning tree that can be used to design a water supply network as well as the telecommunication network. As you know, that when we want to connection we have to put the supply of OFC, like optical fiber communications. The cost of OFC is very high. So when we go for that one, if the network is shortest, definitely the cost will be affected. So and electrical grid also we can apply for there also. So it can use to find path in the map. So algorithm of minimum spanning tree. A minimum spanning tree can be found from a weighted graph by using the algorithm given, like Prim's algorithm as well as the Kruskal algorithm. Let's see the brief description of both of the algorithms listed now. So first one is a Prim's algorithm. It is a greedy algorithm that starts with an empty spanning tree. It is used to find the minimum spanning tree from a graph. The algorithm finds the subset of edges that includes every vertex of the graph such that the sum of the weights of the edges can be minimized. Now talking about the Kruskal algorithm. The algorithm is also used to find the minimum spanning tree for a connected weighted graph. Kruskal algorithm also follows greedy approach, which finds an optimum solution at every stages instead of focusing on a global optimum. Now, how does the Prim's algorithm work? So starting from Prim's algorithm is a greedy algorithm that start from one vertex and continue to add the edges with the smallest weight until the goal is reached. The steps to implement the Prim's algorithm are given as: first, we have to initialize a minimum spanning tree with the randomly chosen vertex. Next, now we have to find all the edges that connect the tree in the above step with the new vertices. From the edges found, select the minimum edges and add it to the tree. Repeat step 2 until the minimum spanning tree is formed. So basically, after using this algorithm, the application of the Prim's algorithm are: Prim's algorithm can be used in network designing. It can be used to make network cycles. It can also be used to lay down electrical wiring cables. So, Prim's algorithm is used to find the minimum spanning tree from a graph. Prim's algorithm finds the subset of edges that includes every vertex of the graph such that the sum of the weights of the edges can be minimized. Prim's algorithm starts with the single node and explore all the adjacent nodes. You can start from any vertices in the graph. So there is not a mandatory you can start on the same vertices, you can start from anywhere. So the condition is you have to explore all the adjacent nodes with all the connecting edges at every step. The edges with the minimal weights causing no cycles is an important point, no cycles in the graph got selected. If the cycle will be formed, you have to disconnect that. You never consider that particular edges from that particular vertices. And the last one, the algorithm. Now discuss about the algorithm as follows. So select the starting vertex. Step 2, repeat step 3 and 4 until there are fringy vertices. Next one is select an edge connecting the tree vertex and fringes vertex that the minimum weight. Next is add the selected edges and the vertex to the minimum spanning tree. That is the end of the loop. We inside the step 2 to step 4 we continue until we don't cover all the vertices, and finally we exit the operation from the algorithms. By the use of algorithm we can understand by this example, like we having a graph. Like a graph, we having a lots of nodes like A, B, C, D, E, and we having lots of weights also 3, 10, 4, 2, 1, 6. Now one by one we can start. You can start from any vertex. Suppose I will take B as a source node. So choose a starting node, that is a B. Now add step 2, at the vertices that are adjacent to A. That edges that connecting the vertices are shown in denoted lines. Step 3, chosen the edges with the minimum weights amongst all of, like B, directly edges between from starting from B, that is a BD, and the rest of the thing, the BD, and add it to the minimum spanning tree. Add the adjacent vertices to D also, that is a C and E. In step 3, choose the edge with the minimum weight among all. In this case, the edges DE and CD are such edges. Add them to minimum spanning tree and explore the adjacent of C. It means E and A. Now step number 4, choose the edge with the minimum weight CA. We can't choose CE as it would cause a cycle in the graph. So you can understand, in an initial step we select only a B, then we consider two edges from B, starting from B to C and B to D. We consider only a B to D because the weight of the B to D is a 4 only. We refuse B to C edge, that's why the weight of that particular edge is 10. Now on the third step, now again when we exploring a D explore to the E also and the C also. The minimum is that one, we consider only the minimum one, that is a E. Now again we exploring C to E also, but when we connecting a E to C, that a cycle will be formed. Otherwise we go for that one. Also we having some we reach to C by a D also. When we go for the E to C having a 6, but D to C having a 2. That's why we continue with the D to C. We don't consider E to C because the weight of the E to C is a 6. That's why we consider only a D to C. So first one B to D, then D to E also, then D to C. That's why the weight is 2. Now the final, there's only single approach to reach the A station from a C only, and the weight is 3. So here in the particular graph, when we considering a spanning tree, here we only one way confusion. The confusion is that to reaching a C, there's two approachable paths to reach this station C, from E also and from D also, but we consider from a D only because the weight of the edge D to C is a minimum as compared to the E to C. That we consider this particular graph. Then we find out the total cost. So the graph produced in the last step, the minimum spanning tree in the graph is shown, and the cost of the minimum spanning tree they calculate as per the last graph. That we addition sum of the edges like 4 plus 2 plus 1 plus 3, that total is the 10 units. Now complexity of Prim's algorithm. Let's the time complexity of the Prim's algorithm. The running time of the Prim's algorithm depends upon using the data structure for the graph and the ordering of edges. Below table shown some choices like Prim's algorithm can be simply implemented by using the adjacency matrix or adjacency list graph representations, and to add the edge with the minimum weight requires the linearly searching of any array of weights. It requires O of mod of V to the square running time. It can be improved further by using the implementation of heap to find the minimum weight edges in the linear loop of the algorithm. The time complexity of the Prim's algorithm of O of E log V, or we can say O of V log V, where E is the number of edges and V is the number of vertices. This is the complexity of Prim's algorithm. Now we discuss the another property of the spanning tree, minimum spanning tree, that is a Kruskal algorithm. So Kruskal algorithm is used to find the minimum spanning tree for a connected weighted graph. The main target of the algorithm is to find the subset of edges by using which we can traverse every vertex of the graph. Kruskal algorithm follows greedy approach which find an optimum solution at every stage instead of focusing on a global optimum. In Kruskal algorithm, we start from edges with the lowest weight and keep adding the edges until the goal is reached. The steps to implement Kruskal algorithm are listed as: you consider all the graph and you should to sort all the edges from lower weight to the higher weight. Now take the edge with the lowest weight and add it to the spanning tree. If the edge to be added creates a cycle, then reject the edge. Continue to add the edge until we reach all vertices. We have to cover all the vertices inside the graph and a minimum spanning tree is created. So the application of the Kruskal algorithms are: Kruskal algorithm can be used to lay out electrical wiring among cities. It also can be used to lay down LAN connection also. So basically we want to put the LAN connection, the building or entire cities, you have to go for the Kruskal algorithm. So the Kruskal algorithm is given as follows. Then step number 1, create a forest in such a way that each graph is a separate tree. In step 2, create a priority queue that contains all the edges of the graph. In step 3, repeat steps 4 and 5 while queue is non-empty. In step 4, remove an edge from queue. In step 5, if all the edges obtained in step 4 connects two different trees, then add it to the forest for combining two trees into one tree. Else discard the edges. You continue with this operation step 3 to 5 until you don't cover all the vertices. So finally when you cover all the vertex, finally the last step is end, or we can say exit from the algorithm. We can understand this algorithm by this example. Here we are having an example, Kruskal algorithm. Examples like we having a lot of vertices like A, B, C, D, E. Also we having a lot of edges as well as the weight also. So what we do first? First we go for the make a table and according to the weights of the edges. So the weight of the edges given as, you take a directly edge from all the edges from the graph like AE, AD, AC, AB, BC, CD, D. You don't go for the E to A because you already covered A to E. So don't select E to A. Once you covered A to E, like A to B, like B to C, you don't cover the vice versa C to B or E to A like that. Only consider only one path because both are indicating the same edges. So we cover all the edges. Also we put the weight like A to E having a weight 5, A to D we having a weight 10, is A to C we having a weight 7, A to B 1, B C 3, C D 4, D E 2. Now what we do? The first step, we have to sort out all the edges according to the weight. So lowest weight will be first and the higher weight will be the last. So as per the ascending order of the weight, we considering the edges by this in the second table like AB, the first weight is only a 1. That's why we provide a first priority or maximum priority to AB because the weight of the edge is only a 1. So first we consider AB, that is a weight 1. Then we consider DE, the weight is 2. BC, the weight is 3. CD, the weight is 4. AE, the weight is 5, AC to weight is 7, and the last one, the maximum weight of the edge is AD, that the weight is 10. How to construct the tree? In step 1, add AB to the minimum spanning tree, then add DE to the minimum spanning tree one by one, then add BC to the minimum spanning tree. The next step is to add AE, but we can't add that as it will cause a cycle. So when we form a cycle, when we connecting some vertices by the edges and it form a cycle, we have to forget it, that one we can't consider. So the next edge to be added is AC, but it can't be added as it will cause a cycle. The next is to be added in AD, but it can't be added as it will contains a cycle. Hence the final minimum spanning tree of the on one which is shown as like that. So is a step number 4, and the cost of the minimum spanning tree is 1 plus 2 plus 3 plus 4 is equals to 10. So by one, we connect all the edges, all the vertices, and the last one representing the minimum spanning tree cost, that the total cost is 10. So the cost is equals to 10, the number of edges in the above tree equal to the number of vertices minus 1. So the algorithm stop here. So the complexity of Kruskal algorithm, so the time complexity of Kruskal algorithm is O of E log E or O of V log V, where E is the number of edges and V is the number of vertices. I hope you understand the concept of spanning tree as well as the minimum spanning tree, and both the application of minimum spanning tree are the Kruskal and Prims, and why we require this minimum spanning tree to establish a network, either electrical network, either land network. By the application of this one, we can reduce the cost of the overall entire structure. So for this tutorial, thank you.